because the actual hardware architecture of supercomputers has a strong impact on which mathematical algorithms are going to be used and are efficient. Let's have a quick look on these models of hardware architecture that are around today. The first is the way memory is distributed. And there is a computational scientist, Michael Flynn, that a few decades ago came up with these categories that you see here. The most important ones are the fundamental model for a serial computer, SIST. It's basically a single instruction, single data that goes back to the famous John von Neumann, who basically came up with this very simple model many decades ago. The first kind of parallel approach were these SIMD machines, single instruction, multiple data. And an example is shown here, the connection machine. In this case, this is a connection machine CM2 that was built in the late 80s by Thinking Machines corporations. I was very lucky at the beginning of my PhD in an earth science department that in 1990 such a computer was purchased, and we could actually develop finite difference type algorithms for these machines. And actually this is the reason why I'm wearing this t-shirt here. The only time I'm wearing a different t-shirt in the course, so you better watch this. So actually what you see here is the design, there's a t-shirt design that led to the design of the computer that you see here in the background, the CM2, that was designed by Tamiko Thiel. You can actually follow this link and look onto the website of how the machine was actually developed. At that time, and that's an interesting fact, the famous physicist Richard Feynman, Nobel Prize winner in physics, was involved in developing the communication scheme for this machine. And it's an indication by itself that at the time he realized how important parallel computing will be. Now, the next model is the multiple instruction, multiple data type model, where in comparison to the previous one, where SIMD, where actually you only had a single instruction that operated on the whole data, and the connection machine in that sense was basically a distributed memory. The MIMD concept is, of course, much more powerful because you can basically distribute many different tasks to each processor, which of course makes the problem harder to actually make a load balancing between the tasks of these different computers. But that's nothing that we're dealing with here in this course. Today, basically all supercomputers are based on this multiple instruction, multiple data concept. So the question basically also is here how to program these machines, and we'll talk a little bit about this later. But let's first also look into the question, how is actually memory accessible when you have such a large number of processing units. So as mentioned before, all modern computers, basically even your smartphone, your laptop, your desktop PC are MIMD machines. They already have multiple processors, maybe not so many, but the large supercomputers now already have hundreds of thousands of different computers, different processors. Now, how does this work? You have CPUs, central processing units, and memory. There are two fundamental models. One is basically you have distributed memory, and you access basically each CPU has its own memory, or which is here shown in the middle, or you have the shared memory concept where basically you have a pool in the middle of memory, and each CPU has at the same time access to this. Of course, in terms of networking, the shared memory model is much is faster and more efficient. So today, actually, on the very large supercomputers, you have a mixing of all these different models. So basically, you often have a local node that has a shared memory system, and then you have many of those distributed where the networking has to basically solve the problem of communication. And that's actually often the bottleneck. So what makes it hard to build a large supercomputer is not so much the actual memory, but it's the networking, it's making the communication between processors efficient. Now, let's just quickly look into how to program in parallel very briefly before we then go into the physics of our problem. Well, let's assume you want to solve a real problem and you have a lot of memory to distribute. How to do that? What kind of programming languages are you using? So, in terms of history, at the very beginning, basically, the compilers or the languages Fortran, C, C++, at the time they all had specific solutions for the hardware that was developed, say for the connection machine or the Cray systems. Today, what is basically used in most research codes is a so-called message passing interface. A very powerful library that basically now exists also for modern languages like Python, that's used to basically access each processor and tell each processor individually what to do. You see a section of a very simple code. Basically, this is the hello world type equivalent for message passing. It looks a little complicated, but in the end, you basically just ask, so what processor am I? What do I have to do? And if you run this with a very simple program, actually you will get, in this case, this is an example with 4 processors, you basically say, I'm processor 0, 1, 2, or 3. Actually also the output will come in random order. It's not that 0 first, 3 at the end. You don't really know which one tells first, hey, I'm processor 3. So, the reason I'm showing that is it's actually, if you parallelize a program, it is quite an overhead in terms of what you need to do. But on the other hand, message passing is a very stable concept that is now basically used in all of research. And that's basically all I want to say about parallel programming. We will focus on Python in this course, and actually there's also a Python MPI library and excellent tutorials in the web where you can play around with some simple examples of parallel programming. One more concept about parallel programming before we move on. Let's say if you have a parallel computer with 100,000 cores and you want to parallelize some specific tasks, is there an idea of how efficient this will be in the end? There's a very simple, quite shocking equation that will tell you that. Now let's assume that you have a problem that has basically the amount of parallelism P in a percentage is given as, for example, 99%. So 99% of your algorithm can be parallelized. And so the serial part would be 1%. Actually, often I/O, input-output, takes a lot of, is actually hard to parallelize, which is, today there are solutions, but often I/O is a bottleneck. Now, there is an equation that was developed by computational scientists that gives you the speed up as a function of number of processors. So it's the inverse of the capital P divided by N is the number of processors, plus S. Now, there's a couple of examples given here in the graph, and it's actually quite shocking, because you can see that if that equation is correct, then actually your efficiency is quickly leveling off. That means if you use more processors, you don't really get much faster. And that's actually really challenging, because it tells you that actually to really make use of large supercomputers, the amount of parallelism you have really has to be 99.999 as much as possible %, and then you can efficiently make use of supercomputers. on that note, actually, if you apply for CPU hours or GPU hours on large supercomputing systems, this is exactly what you have to demonstrate. You have to demonstrate that, and this is called scaling, that your algorithm is efficiently scaling on large supercomputers. That means if you use, let's say, 100,000 processors, you actually also are close to 100,000 times faster than using a single CPU, and that's actually quite hard.